Okay. I think I just got it to work. Okay. Do you all see something on your screen? Yep. Okay. Alright, so I'm actually going to slide this over. There are so many things that are open on my computer screen right now, so just bear with me 30 seconds. Okay. This is my
I think I just got it to work.
Stream Studio. I need to open Smart Notebook. File open. I had to restart my computer, so just bear with me. Do you all see something on your screen? Yep. Okay. Alright, so I'm actually going to slide this over. There are so many things that are open on my computer screen right now, so just bear with me 30 seconds. Okay. Alright, so that's going to be up and running in a minute. I don't want this, and I need you. I need you. And I had to restart my computer, so just bear with me. Do you all see something on your screen? Yep.
I got two screens running.
Alright, so I'm actually going to slide this over. There are so many things that are open on my
coming
computer screen
back.
right now, so just bear with me 30 seconds.
Okay. Alright, so
That's going to be up and running in a minute. Okay.
I don't want this.
I think I got this. I need you. Alright, I do not need a copy of you watching me. Watching you. I don't need that. Okay. I don't need this. Yes, this is what was not working. I could not access this, which gives me the key in order to stream. Alright, so hi. I'm so sorry that took so long. That was 20 minutes in the waiting. And I promise you that it won't happen that way again. Welcome. I want to show you a couple things really quick before we dive into the content. On the website, the new drop-down menu tab that's for you, there's a link called Online Instruction, and this is where I'm going to be providing for you the assignments. And I know it says by noon. I feel like, you know, that's a little fluid depending on when I'm going to be streaming, but that gives you enough time in order to do whatever it is that I'm asking you to do so that we can have a conversation about it later in the day. And I'm sorry that this particular stream is so late. It just happens to be the time that I was able to get all my children into bed, and I was able to actually dedicate enough time to talk to you and give you all the information you need, go through the chemistry, and then we can definitely try to get streams going sometime over the course of the day. But it was just a little bit easier the first time to do it a little bit later so that we can all be on the same page. So on the website, this is what I had asked you to do. Over the weekend, there was a lab that you were supposed to be sharing data for, and this is the Google Excel sheet. And it looks like there is one piece of data currently that's missing. I don't need to do that. That's fine. Okay, there's one piece of data here that's missing, so when you guys go to write your lab reports, I'm just waiting for that one piece of data to get in here. When you go to write your lab report, I'm going to just add, which I can't edit on this because I'm not currently in my account. Let me just get in my account really quick. Manager account. Okay. Oh no. It's not the one I want either. Yeah, this is not going to work right now. Okay, when you go to do this, I'm going to ask that you, and I can't type, average the value. So you want an average room temperature, an average warm temperature, and when you go to do your data, you're going to be averaging the data sets from across all three classes. So that was what I asked you to do over the weekend. Still waiting for this one data point, and I'm just looking right now at, oh no, there's an echo. Okay, hold on a minute. There's an echo, a very big echo. Huge echo. Alright, hold on a minute. Is the echo any better? Alright, I'm just pulling you guys over here for a minute so I can see you on the chat bar. Okay. Let me just check out this chat bar. Is the echo any better? Okay, good. The reason why the echo was so loud is because I had turned the volume all the way up while trying to watch some sort of tutorial as to how to get it to get my stream back going. And it turns out that when I put the headphones in and I had a second computer screen going, I had unplugged the speakers, so there was no noise. Okay, I do not hear an echo. Fantastic. All right, so echo is fixed. So back to this. I'm going to ask you that you put your data in, and we're going to average the three sets of data from all three classes. Still waiting for this data point to get in so that we can finalize this data and we can write our lab report. So that's actually Tyler's group in period 9. Tyler, I think Danielle's in that group. Brianna, Jess, who else? Olivia, and I know we had split some people up, and there's somebody else who's in that group from the other table, but either way, I just need that last piece of data in. Somebody was asking me, when are we going to make the lab reports due? Because normally they're due at Tuesday at 6 a.m. We won't go Tuesday 6 a.m. That's just insane. I will update this, and I have to make myself a little list of things that I am going to need to have to do. And that I can't do while I'm currently streaming. I'm going to be posting a link as soon as I finish this. We're gonna go turn it in, and let's go Wednesday at noon, which gives people enough time to write, to do what they gotta do, to submit, to turn it in, and for the last group to get their data in so that we can, have all the data that you need to write your lab report. People were panicking. They're like, 6 a.m. That's crazy. We're not going to go 6 a.m. on that one just because we're not in school. And I hope that at 6 a.m. you're all still sleeping so that we don't have to worry about that time. So we'll go Wednesday at noon. I think that that's more than fair. And I'm just checking right now to look at the comment bar. Yep. Okay. All right. So the next thing I'm going to throw out here is that the way I'm going to work this is that I'm going to be putting on the website when things are due. So like this is Monday. These are the things that I would like you to do on Monday, and I would suggest that you do them in order. So you're going to read the following pages on Equilbrium. There was a set of pages that I had scanned from the review book that I had posted, and usually it's going to be some sort of short reading, if it's a reading, and then print and complete the Regents questions. These are the things that I'm going to have you do on that day. So Monday, these are the things you're doing. It's not like this is Monday's homework. This is more like the things and tasks that should be completed on that day. And they should be done in order by the time the podcast happens, because the podcast is going to tie everything up and put it all together for you so that you're getting my description of whatever is happening in that reading that you're talking about, or we can go over whatever practice questions that I'm giving you. I'm going to start off in the beginning probably having you do some readings, do some practice questions. If it's not a reading like tomorrow's work, there is a PDQ where you're going to watch a series of short clips on something called Le Chatelier's principle. Other people who were explaining Le Chatelier, I want you to have some sort of familiarity with it, so that when I come in and I do my podcast, it's not completely brand new to you. Because usually Le Chatelier is something that people struggle with. It's a difficult concept. So when I head into Le Chatelier on Tuesday, you're going to do a PDQ before. It should take you about 20-30 minutes of, watching some videos, taking some notes. And then I'm going to stream on Le Chatelier later in the day, probably about the same time tomorrow, only because I have the kids tomorrow and they're running around like absolute lunatics, and the only time I really can sit down and give you dedicated time that can really be chemistry, that I can answer questions and do it in a way that makes sense to you live, would be later in the day. So I'm thinking tomorrow will probably be a stream later in the day, probably around 8:30, 9 o'clock. Probably the rest of this week, if I stream, it'll either be like earlier in the day, like 9 or 10 in the morning. Otherwise, it's going to have to be about 9 o'clock at night. And I'm actually going to send out a Google survey to ask you, like, what times are better for you? Like, if this 9 p.m. thing works out, because you're not going anywhere, you're not doing anything, then this is probably the best time for me. Otherwise, if this is absolutely impossible for most of you, this 9 p.m. time, then we don't have to do it at this time. And either way, whatever goes on here that we talk about will always be recorded and saved to YouTube, so that you can always have it when you can watch it whenever you want, and the live chat bar will be recorded so you can see what's going on. Okay, so with that being said, we should also just talk really quick about how I'm going to have you do the assignments. Anything that you were reading or working on, like the pages in the review book, the Regents set, always print them, and you're going to file them in your binder. Like the reading should go in your notes. The Regents set should go into like your classwork section, like you would if we were doing in class. Any sort of notes that you take on the podcast, I'm going to have you take those notes on a piece of loose leaf paper that's going to get tucked into your notebook, so that, eventually one day when we return back to school, I can see that you did take notes and you did attend the podcast and you wrote some stuff down that we were talking about. So, last thing before we get into the actual content of chemistry, let's just talk about tomorrow's assignment. You're going to complete this PDQ. watch all the videos, take some notes. You're gonna have a hard time. Do the best you possibly can while watching these videos. My job later in the day will be to have another podcast for you so we can talk about Le Chatelier. Okay, so let me just pause really quick, and I am checking the chat bar really quick, and I see nothing. Can I get an affirmative? Just start typing in the chat bar yes, smiley faces, thumbs up, whatever it is, so that I know that you're still with me. And I can start getting into the chemistry content. Just start giving me signs of life over there, people, because I see nothing on the chat bar changing any day now. Okay. Alright. It's my notebook. Anything on the chat bar? Nice emoji, Lexi. I love it. Okay, so I'm obviously seeing that there's a delay. There's about a 20-second delay, which makes me feel better that you guys are not ignoring me. Oh, there you all are. That's not what I meant to do. Let me put you over on the screen. Okay, so here we go. Let's talk equilibrium. Okay, gonna hide this, and let's talk equilibrium, because that's the reason why we're here today. You read in the review book some pages on equilibrium, and I think it's actually really, really fitting that the topic that we are about to discuss in the middle of all this crazy, crazy things going on in the world is that the only thing constant in this world is change. And that is the biggest, truest statement, I feel like, in science. We look at things and they appear to be staying the same. But on the microscopic, submicroscopic level, things are constantly changing. It's just that to the naked eye, we're not perceiving those changes. And one of the words that very, very often is associated with the word equilibrium, and it comes from your living environment time, and it usually precedes this word. There's usually a little descriptor over here. And the word that they use in front of equilibrium is dynamic, which I wish I had a smart notebook, like a actual, like a smart board that I could actually write on, because this is actually a little bit difficult. It's not how you spell dynamic. Hold on. Dynamic. That's an N. Dynamic. Okay, and the word dynamic means constantly changing. Okay, constantly changing in the sense that if you look at the actual makeup of what is going on, the particles are constantly changing, but to the naked eye, it looks like everything is staying the same. The only thing constant in this world is change, and I just feel like in the middle of everything going on right now, where things are just all over the place, and it seems like everything is changing all over around you, there is definitely constant things that are just being held true, and that's kind of where we're going here. This is kind of a massive shift in the equilibrium that we're seeing in our everyday lives with everything that's going on, and we're kind of like on an upswing or a downswing, whatever swing it is that we're looking at. Either way, we're shifting out of the norm of equilibrium, but we will be returning back to this equilibrium, hopefully really, really soon. The story that I want to tell with you about equilibrium, and I'm going to have you guys work through the definition with me. Oh, there's a whole bunch of orders of business on here. See, I even typed up orders of business. This is everything I talked to you about in the beginning. We'll come back to this at the end, and we'll check the Regents questions at the end. The equilibrium concept that I want to go over with you, that I want to start with, is actually a non-science equilibrium story. So I want you to pretend for a second that there's a school bus, and on that school bus, the maximum capacity for students, so max capacity is 10 students. You can only have 10 students on this bus. And right now there are 10 students that are on this bus. That's what's happening. The bus driver's like, hey, 10 students, you're on the bus. And the bus stops When the bus stops, two students, and I'm going to draw for you because I'm really good at stick figure drawing. Two students get off the bus. You have a really long neck. And you're super happy. Yeah, you don't look that happy. Two students get off the bus. This one has a nose, that one doesn't. Okay, and you have a super long neck too. These two students, and a leg, super long leg. Okay, these two students get off the bus, which means when two students get off the bus, there's no longer 10 students. There's now 8 students. But that's not the only thing that happens at the bus stop. Okay, at the bus stop, not only do 2 students get off the bus, 2 other students, there you are, get on the bus. There you are. You have a very large head. Okay, these 2 students get on the bus. Even though 2 students got off, which would make the number of students 8, well, 2 students just got back on the bus, which brings this value back up to 10. This bus is in equilibrium. I want you to take a minute, and I am going to just watch the stream on the side right now, and I'm going to watch your chat bar. I want you to come up with a reason as to why this system is in equilibrium. I just want you to start typing. There's no right or wrong answers. I'm waiting for you to tell me a few things about what's going on this bus. Talk to me. I'm looking at the chat bar while I'm waiting. Waiting for you all to start typing some stuff. Why is this in equilibrium? Okay, I see Audrey is writing balance. Okay, Audrey, I'm gonna have you elaborate on that. Oh, I like that one, Dylan. Constantly changing. The rate of student dismount. Whew, I love it. Oh god, the headphones just came out. The rate of student dismount is equal to the rate at which students board the bus. Justin, I love it. Absolutely love it. Jordana says 2 on, 2 off. Okay, excellent. I'm seeing the word balance again. I'm seeing equal change. I'm seeing balance. Constant change is done to maintain an equilibrium. Okay, so I'm gonna kind of tie a few things here. Dylan, okay, I want you to answer this question because you're the one that threw down with this. You said constantly changing. Please explain to me, what is constantly changing? I want Ari, who just wrote, they balance each other out. Ari, what do you mean when you say they balance each other out? What is being balanced out? Okay, I'm looking right now at Olivia. She says there's a pace in which the change is equal. You are absolutely all saying beautiful things. You're telling me everything that I'm looking for, and I'm going to give you the formal wording in a minute, but you're hitting every point that I wanted you to get out of this little story. Okay, and I'm waiting for Dylan to come back to me, and I'm waiting for Ari to come back to me, because those are the 2 people that I had asked to explain and elaborate what it is that they were saying. You all said beautiful things, but I just picked 2 random people that had said them. Alright, so Ari is writing that the students, because so the students are going to be the ones that are equal. So because 2 students came on the bus as 2 students were coming off, I'm going to give you an official word for that because I feel like that's Olivia's comment. There's a pace. We don't use the word pace, we use something different. I'm going to get there in a minute. Allie Stern writes, Audrey, can you please explain balance? That's actually a great question. Where is this system balanced? Dylan. There's an equal change. I take 2 cookies from the jar, 2 cookies go back in the jar. Dylan, I don't know what house you live in, but cookies never go back into the jar on their own. But yes, I completely agree with you. At any given time, the number of cookies in your story would be equal inside of the jar. Like, the number of the cookies that you have are going to be the same in the jar if you're constantly exchanging the number of cookies in and out. The cookie jars in my house never reach an equilibrium because there are definitely more cookies leaving the cookie jar than anyone is ever putting back into that jar at any given moment. So let me give you some official terms here. We call this over here, should probably go with a different color besides yellow because the bus is yellow. We call these arrows, the blue arrows, the rate of exchange. So let me get some typing going on here. Did I type this? Yeah, but I'm gonna formally put it on the bottom in a minute, and I need to shrink this down really small so we can get it all in. We call these blue arrows the rate. Let me go equals the rate of exchange. And in this story, there are 2 students that are getting on the bus, and there are 2 students that are getting off of the bus. The rate of exchange here is equal. 2 on, 2 off. And the way I want to remember this is that the rate of exchange with an E always needs to be equal with an E. Let's actually underline that at the same time too. Rate of exchange is equal, and I'm going to capitalize this E just to add to the alliteration here, bold and underline. The rate, which ends with an E, of exchange with an E needs to be equal with an E if you are in equilibrium. Rate of exchange is equal. Now, what I think Olivia was going on with, I'm just looking really quick at the sidebar. I think what Olivia was saying, Olivia had used the word pace. Okay, that was Olivia's word. Pace, which was Olivia's word. Olivia, did I spell your name right? Nope. Oh, look at all these ways to spell check your name, but clearly Olivia's right. Just don't know why they would underline. Okay, sorry, got sidetracked. Okay, Olivia uses the word pace, and that's a great word. It's not the scientific word, but the pacing at which students are going on and students going off is equal, which keeps this system in equilibrium. Now, here is the other word or the other idea, which I think is what some of you were trying to get at when you said the word balance. The rate of exchange is equal. The rate of exchange is what we would maybe say balance, but there's a bigger balance here. Equal does not necessarily mean balanced, believe it or not. At any given time, in my little story, there are 2 students that are off of the bus. At any given time, whether they're getting on, they're getting off, there are 2 students outside of the bus. At any given time, even though this number is momentarily changing, at any given time, you have 10 students who are on the bus. This is what I think you guys are referring to when you're talking about the balance that exists. When the rate of exchange is equal, I'm going to add in here, when the rate of exchange is equal, let's actually highlight this too, but we're going to highlight in a different color. Let's highlight this in pink. Let's go pink. When the rate of exchange is equal, there is a balance that is developed. So let me go down here, and I want to talk about these pink numbers that are present. At any given time, if you were to take a snapshot as to what's going on here, there are 2 students that are off of this bus, 2. There are 10 students that are on the bus. Is 10 equal to the number 2? I mean, I know Miss Chilton's not in my house, who's my math expert, but I'm pretty sure if I ask a math expert, like 2 is not equal to 10. They're not equal. They're not changing. They're staying constant. They're staying balanced, but balance does not necessarily mean equality. When you start talking about a balance or you start talking about an equilibrium, those 2 values do not need to be equal to each other. Those 2 values just need to stay constant in relation to each other. They might change, momentarily. It might be dynamic momentarily, but if you were to look at this overall system, there's 2 students off and there's 2 students on this bus pretty much at all times. It's just the identity of those students are changing, who's on and who's off. So if I were to compare the number 2 and the number 10, they're not equal to each other. We call these values in chemistry the concentration. The concentration of the students on the bus is always going to be 10. The concentration of students off the bus is going to be 2. They're constantly changing which students are on the bus and off the bus, but at any given moment, those values of concentration are going to remain constant. That is the idea of balance that I think you are getting at. And the way I want to remember this is that concentration, CON, bold, underline, it must remain constant, CON, bold, underline. And this is one of those things in the curriculum that is classic Turkey on Thanksgiving. Okay, I guarantee you that there is going to be some question somewhere on equilibrium, and they're going to talk to you about rates of chemical change, and the rate of exchange with an E always has to be equal. That's like what Dylan said with the cookies, like 2 cookies in the jar, 2 cookies coming out of the jar. That's the rate. In this story, you have 2 students getting on the bus, 2 students get off the bus. That is a rate or a pace of change. However, the concentration or the amount of those given students on the bus or off the bus is not equal to each other. They just have to remain constant in relationship to each other. I'm gonna pause for a minute. I'm gonna just take a look at the side chat bar. These 2 statements are, like I said, classic Turkey on Thanksgiving that the Regents exam loves. Look at all these cute hearts. Okay, the Regents exam loves these statements over here. Oh, I didn't mean to put you over the statement. They love these 2 statements. So wrap your mind over them. Take a minute. I just want to look at the sidebar, and I'm going to start looking for you to give me some thumbs up, some smiley faces, whatever it is, so that I can see that you are with me right now. Okay. All right. I see you on the chat bar. Good. 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 Okay. So many thumbs up. I feel so accomplished. Okay. Good. All right. So let's move on. Moving on. So, 2 statements. The concentration must remain constant because the rate of exchange is equal. When the rate of exchange is no longer equal, that's when things start to change. That would be equivalent of, well, 2 students get off the bus, but only 1 gets on. This is no longer in equilibrium. It would be the equivalent of like my house, where the cookie jar never reaches a status of equilibrium, even a dynamic one, because there are more people who are taking the cookies out of the jar than I could ever refill that jar, which means at any given moment, my cookie jar is probably empty because my kids are constantly, ransacking the cookie jar and taking more cookies out than I could be refilling at the same rate. Let's get into some actual chemistry. So, not orders of business. Okay, let's talk about phase equilibrium, because the first equilibrium you are responsible. Oh no, hold on. The echo is back. Well, you know what? I covered the microphone for a minute because I was drinking coffee and I didn't want you guys all hearing me swallow. So, I think that could be what the echo was. I'm just going to wait for you to tell me if it's still echoey before I move on. Give me a thumbs up, Sam. Let me know the echo's gone. And there's a 30-second delay, so I'm sorry that sometimes I feel like you're waiting for me or I'm waiting for you, but there's always a 30-second delay. I don't hear an echo. Okay, good. Good, I'm happy to hear that. Okay, phase equilibrium, because this is where the chemistry actually comes into play. In the beginning of the year, we did things like that's not a highlighter, I want a calligraphy pen, where we talked about things like you're in the liquid phase. And let's go water, and I want to shrink this calligraphy pen really thin. Okay, let's go water. You have water in the liquid phase. Okay, water particles that are moving around. Let me actually a little thicker on these guys. We have water particles that are in the liquid phase. They're hanging on the liquid phase, and over time, some of these little particles may decide, you know what, I really don't want to be a liquid anymore. I think I'm gonna turn into a gas. Which, by the way, if this is going to achieve an equilibrium, if this is going to achieve an equilibrium and I have a gas, well, right now the gas is going to be free to leave this container because I have not sealed the container. So what I really need to do if I want to achieve a phase equilibrium and do that with a gas, and I am going to need to seal this container. So let's actually do that right now. I need a line. Here we go. And I'm going to seal this container so that these gas particles can't get out. So right now, there are gas particles that are in this container. And let's say that there are 3 gas particles that are in this container. So let's start labeling. Let's call this 3 gas particles. And I'm sorry for my typing because I'm using a mouse to do this while writing. And I have 6 liquid particles. 6 liquid. Well, if this is going to achieve an equilibrium, and I have this liquid who is turning into a gas, that would now mean that there's no longer 6 liquid particles because this guy just became this actually was 2 to start. Hold on one second. I gotta draw this guy. Let's call this, there were 3 gas particles, 1, 2, 3. I probably just confused you. Hold on a minute. Okay. This green arrow I'm just gonna take out for a minute. So I guarantee you I probably just lost you. It's not my goal. Okay, let me start again. There are 3 gas particles, 1, 2, 3 in the gas phase. There are 1, 2, 3, 4, 5, 6 liquid particles in the liquid phase. And over the course of time, a liquid is going to have enough kinetic energy to decide, I don't really want to be a liquid anymore. I'm going to become a gas. So let's gas this particle up. And if that's what happens, this guy is now gone, which means there are no longer 6 liquid particles. There's now 5 of them. And there's no longer 3 gas particles. There's now 4 of them. But this is in equilibrium. These concentrations are not going to stay constant, but if we're in equilibrium, they will go back to being constant if the rate of exchange is equal. Right now, there is a liquid who turned into a gas. Well, then if that's the case and we're in equilibrium, there has to be a gas particle who says, I really don't want to be a gas anymore. I'm going to become a liquid. Which means momentarily this number shifts, but within, I don't know, not even something like, seconds or milliseconds, something to the naked eye that we can't even perceive, this now drops back to a 3, and this now bumps back up to a 6, and at any given time, the initial concentration of 3 is staying constant. This initial concentration of 6 is staying constant because we are in an equilibrium. I'm going to pause for a minute. I'm going to ask you, you're going to start typing in the sidebar in a minute, why do these concentrations stay constant in this picture? want you guys to start typing in the sidebar when you're ready. Why are these concentrations staying constant? Okay, Dylan says at the end of the day, I still have 9 total. I agree with you. But I would still have 9 total if I had 4 and 5. So that's not the reason why this is in equilibrium. Why is the concentration of this gas, even though it jumped to 4, it went back to 3? Why is this concentration, which dropped down to 5, go back to 6? Why is this concentration of 3 and 6 staying constant at 3 and 6? Okay, Ari says it's because the container is closed so that they become a gas and then go back to a liquid. Ari, I agree with you. But is it the same particle that's going from liquid to gas that is going from gas to liquid? That is the dynamic component, the constantly changing. At any given moment, is the identity of these particles the same as these? Like, this guy was just a liquid, became a gas. This guy was a gas who became a liquid. They're not the same particles. That's the dynamic component. Justin, you are 100% right. The rate of exchange is equal. When you are talking about the rate of exchange and you're saying constant rate, Jordana, I want you to substitute the word constant with equal, because the word equal means mathematically the same exact number. The number of liquid turning into gas is 1. Like, we have a 1 liquid turning to gas, and I should probably do this in a different color. 1 liquid turning into a gas, as a gas is turning back to a liquid, that is 1 particle. The rate of exchange over here is 1 to 1. The rate is 1. However, the concentration of 3, and I should go a completely different color on this, bear with me one second. The concentration, which is my purple values, they're staying constant. They are not equal. 3 does not equal 6. Concentration and constant are very different words. I want you in the habit of using the word equal to describe rate, because rate has to be equal 1 to 1 or 2 to 2 or 3 to 3, whatever it is. Whereas the exchange, not the exchange, the concentration of 6 and 3 do not need to be equal to each other. I'm going to go down here. Actually, it's a lie. Let me just clean this really quick because there's a lot of scribbling going on. It kind of looks like my board in class. Let me get rid of this. I should probably not have gotten rid of that. 6. So let me get that back in here. This was 6. It's a lie. This was 3. And this was 6. And we're going to make this purple so it's clear to see. Let's type this out. Let me shrink this down. Alright, so here we go. This system reaches equilibrium, which means that the concentration of liquid, which is at any given moment 6. That's not high school particles. 6. The concentration of liquid, which is 6, and the concentration of gas, which is 3, are going to remain constant. Let me just drag this over. They are going to remain constant. Let me put this underneath. Concentration remains. That's not what I want to do. I just want to make you larger. Why won't you let me do that? Fine. Shrink you down. The concentration of these particles, so the concentration of liquid stays at 6. Concentration of liquid, and the concentration of the gas is going to remain constant. Why is this staying at 3 to 6? Because the rate of liquid turning to gas, so liquid arrow gas, is equal to the rate of gas turning back into a liquid. The rate of liquid turning into a gas is 1 in my story, and that is equal to the rate of gas turning back into a liquid, which is also 1 in my story. Rate, and let's go rate of exchange. So rate with a E, exchange with a E, has to be equal with an E. Okay, let's pause for a minute because I had snipped down here a question from the practice set of questions that you were working on, that you had worked on before. Which balance equation represents a phase equilibrium? Which means you have to have 2 different phases in your question. Like, you gotta have 2 different phases. And the phases are only appropriate when you're talking phase, and I should put this in here. You are talking about solid, liquid, gas. Please notice aqueous is not in this little story because there is a completely different type of equilibrium for aqueous things. This is strictly solid, liquid, and gas that we're looking at. So I need to have different phases. If I take a look at answer choice number 1, I got gas, 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 not a phase equilibrium. We got gas, gas, not a phase equilibrium. Oh, look, not a phase equilibrium. So the only answer choice I have left is answer choice C, which is chlorine gas and chlorine liquid. And the really big thing here is not only do you need to have 2 different phases, the identity of the substance needs to be the same. This was chlorine, and this is a physical phase change, which means the identity of these substances are the same. I'm going to go back up here for a minute. When this liquid turned into a gas, like, did it change its chemical identity? Did it change from water to something completely different? That would be a chemical equilibrium. Like, that would be a chemical change. This is a physical change because it's a phase equilibrium. Just gonna go over here for a minute. In a phase equilibrium, the identity, that was supposed to be a D. Looks nothing like a D. Sorry. The identity of the substance needs to remain the same. And I'm not gonna try like pretend to be able to write all that out with my mouse. The identity of the substance needs to remain the same. I'm gonna pause for a minute. Just give me the thumbs up that we're ready to move on to solution equilibrium. And we're gonna move on. Just give me the thumbs up in the sidebar so we know we're ready to go. Okay. All right, moving on. Solution equilibrium. So, the deal with solution equilibrium is you must have a solution. That sounds kind of like the sky is blue because the sky is blue, but you have to have a solution. And this solution, it's really, really important that this solution is saturated. So, if you're talking about a saturated solution, saturated solution, it has to be saturated with excess precipitate. Okay, so saturated with excess precipitate, which means it has to be over the line from table G. This doesn't work if you're not over the line, and it doesn't work if you do not have solid precipitate. If you are super saturated, it's not going to work either because you're not going to have different phases of matter. So in this little story, let's say for a second, and I'm going to go over here and I'm going to start typing a few things in. And we should shrink you down to like size 14 font. Okay, let's say that maximum capacity for this solution capacity is 10. Max capacity is 10. Let's go 5. I don't really feel like drawing. Max capacity is 5. And you as a chemist, you decide to add 7 grams, and this should say 5 grams. Max capacity is 5 grams, or 5 circles, and you decide to add 7 grams. I'm going to pause for a minute, and I'm going to let you on the sidebar. I want you to tell me, what would you expect to happen if max capacity is 5 and you decide to add 7 grams? Like, what's going to happen in this story? I'm going to wait for you on the sidebar to tell me what I should be drawing. Okay. So 5 grams dissolve, 2 grams remain solid on the bottom, precipitate, you will precipitate. I totally agree with you. 5 in the liquid phase. Okay, be careful, Alexa, it's not the liquid phase, it's the aqueous phase because it is dissolved into water. Okay, Scott says you will have a supersaturated solution. Scott, this would be supersaturated if I were to have extenuating circumstances where I have the ability to play God and get more dissolved into the solution that I'm supposed to. We're going to pretend for a second that this is an everyday scenario where you are not playing God and you're not getting extra into the solution that you're not supposed to. The key here is, I really should have said what should happen. Like, what would you predict to happen if this was normal everyday circumstances? And if max capacity is 5, you are going to get 5 of these particles that are going to dissolve. So artistic sketch of 5 particles. Here I go. 5 particles. 1. Let me go a different color. 1, 2, 3, 4, 5. These particles are not in the liquid phase. They are in the aqueous phase because they are physically dissolved into water. That's the reason why this is solution in equilibrium, not a phase equilibrium. It's not a pure phase. It's not solid, liquid, gas. Okay, I'm just checking out the sidebar really quick. And it says, does energy present matter? 3, 4, 5. I'm hearing 2 voices. Oh no. Okay, hold on. Okay, wait. Okay, wait. I'm gonna pause for a minute. Tell me if the echo went away. This is solution in equilibrium, not a phase equilibrium. It's not a pure phase. It's not solid, liquid. Tell me if this echo got any better. Okay, I'm just checking out the sidebar really quick. And it says, does energy present matter? I'm hearing 2 voices. Oh no. Okay, hold on. Okay, wait. Okay, wait. Okay, I'm still waiting for you to tell me if the echo got better. Tell me if this echo got any better. Okay, I'm just checking out the sidebar really quick. And it says, does energy present matter? Better yet still present. Okay, hold on 1 second. Okay, how about now? Tell me if the echo got better. How about now? I'm just going to lower my volume on my computer too. It's still there. Okay, I have no idea why the echo's still here. Better yet still present. Okay, hold on 1 second. Alright, I'm going to talk for a few more minutes. If it becomes absolutely unbearable, just start typing again in the sidebar and let me know. These particles that I
How
have
about
dissolved
now?
right now, they're in the aqueous
How
phase,
about now?
which means that there should be 2 particles that cannot dissolve, which puts them into the solid phase on the bottom.
Still there.
You have 2 solid precipitate particles on the
I have
bottom.
no idea where the echo
So
was.
5 are in the aqueous phase,
Hmm.
and 2 are in the solid phase. Just checking the sidebar. Still there.
Alright, I'm gonna talk for a few more minutes. If it becomes absolutely unbearable,
Okay,
just start
you
typing
still
again
hear
in the
it.
sidebar
Still
and let
hear
me
it.
know.
Let me
These
turn my
particles that I
volume
have-
all the way down.
which means that there should be
Oh, you know what?
that cannot dissolve.
I think it's because I might have opened what you're seeing.
You have 2 solid precipitate particles.
Let me close that. I think I might have just solved the problem. Justin, you're 100% right. I had opened my live stream. You know what? I'm going to do it, but I'm going to mute it because that is the problem. I wanted to see how long of a delay it was between what you're seeing and what I'm seeing. So I opened what you're seeing. I think I'm like a 30-second head start on you. So the problem was when I opened what you're seeing, it's playing and I didn't mute it and I just muted it. So I think I fixed the problem. I think I fixed it. Okay. So just give me the thumbs up because I muted it on my end. I muted what you're seeing so that you shouldn't hear that anymore. Just give me the thumbs up in the sidebar that we're ready to move on. Waiting for the thumbs up. Okay, good. I'm so sorry about that. Like I said, I just wanted to see how far behind you were. Yeah. Okay. All right, I'm so sorry. All right, so back to me. In this little diagram, we have 5 particles that are dissolved, and we have 2 particles that are solid. So 5 and 2. And at any given moment, some of these solid particles say, you know what, I really don't want to be solid anymore. I want to become... I don't want to put that there. I want to become aqueous. So this guy decides, I'm going to become aqueous, which means there are now 6 aqueous particles. But this is an equilibrium, which means that the concentrations need to remain constant. So this guy over here is that, and this guy's now gone, which means this is now only 1 solid on the bottom. This guy who's aqueous goes, I really don't want to be aqueous anymore. I think I now want to become solid, which then drops this number back to 5. This goes back to 2. The concentrations in this little story are still remaining constant. So I'm going to go in here. I'm going to add to this little story. The concentration of aqueous in this story is still 5. So concentration aqueous is 5. The concentration of the solid will return back to 2. The concentrations are remaining constant. 5 is not equal to 2. There is a balance of 5 and 2. It remains 5 and 2 over the course of this little story, but 2 does not equal 5. They are not equal to each other. Their actual values are just remaining constant in relationship to each other. And once again, the reason why they are staying constant, I'm just going to wait for you on the sidebar. I want you to finish this statement. They remain constant because I am looking for you to give me the answer on the sidebar, and I'm going to be wrapping this up in the next 5 minutes. We're hitting chemical equilibrium. I'm going to give you the answers to the homework and we're going to call this a night. I promise you it won't be so long every night. We just had a lot of technical difficulties this evening. So finish that sentence for me. I'm going to hit chemical equilibrium in a minute and we're moving on. Go ahead, finish this for me. Waiting for the end of the sentence. Because why is this remaining constant? Justin said it. Because the rate of exchange is equal. Justin, where specifically is this rate of exchange equal? Okay, I love it. I love all these up arrows. Where is the rate of exchange equal? Somebody tell me where you see that equal rate of exchange. Because the rate of exchange is equal and constant. Good. They occur at equal rates and as saturate, the exchange is equal. Yes, tell me where the rate of exchange is equal. Like specifically, where is this? Where is there an equal exchange? Excellent. The exchange from aqueous to solid. Beautiful, Justin. So the rate of exchange is equal every time a solid is turning into aqueous. And this is not typing. Every time a solid is turning into aqueous, comma, an aqueous is turning right back into a solid. Phenomenal. Beautiful. Let's move on with life. Okay, the final type of equilibrium that you are responsible for knowing is a chemical equilibrium. So in this little story, let's say we have 100, and that's really a thick. Let's say we have 100 pieces of reactants and we have 10 pieces of product. This reaches equilibrium. So at any given moment, we have 100 reactants, we have 10 products being formed. This is in a chemical equilibrium, which means every time one of these reactants turns into a product, so this would drop down to 99, we would then produce more. Every time a reactant is broken down, or that's a lie, every time a reactant is put together, it's going to make a product, which would be another piece of product, now making this 11. These concentrations are not staying constant, but we're saying this is an equilibrium right now, so they have to go back to being constant. So this would be the forward reaction. We have 99, now we have 11. Well, at any given moment, a different piece of product is being broken down, which drops this back to 10 to make more reactant, which brings us back up to 100. So in this little story over here, at any given moment, the concentration of reactant to product is going to be 110. Like that is why this is an equilibrium. The reason why this is in chemical equilibrium, my dogs are going nuts right now. The reason why that this is in chemical equilibrium is because the rate of the forward reaction is equal to the rate of exchange in the reverse reaction. So if I were to call this A, and let's call this B, sometimes we have seen in chemistry class that reactions are written either like this, with halvesies arrows. This is implying that A is getting turned into B at the same time and the same rate that B is being turned back into A. This is a chemical equilibrium symbol. Sometimes this is written as a double-sided arrow, which means it's reversible. And the rate of exchange here would have to be equal to keep these concentrations constant. The moral of the story here is, no matter which little scenario you talk about, this rate of exchange is equal, concentrations are constant. You can talk about it in a solution equilibrium, but the key here is that this only works if you have excess precipitate, so you can exchange. This doesn't work if there's nothing to exchange with. The reason why it works here is because you have reactants that can be exchanged for product, and product that can be exchanged back to a reactant. In a phase equilibrium, you have two different phases that can exchange to keep the concentrations constant. The moral of the story here is there's only one thing constant in this world, and it's change. And the reason why this works, this constant, is because the rate of change or the rate of exchange has to be equal, which keeps the concentrations of whatever it is that we are talking about constant. So, the final thing I'm leaving you with tonight. My God, my dogs are barking so loud right now. Okay, the final thing I want to leave you with are the answers to the Regents questions. This is them. Hopefully you did them. Take a minute. Check your work. I'm reading the sidebar. Okay. I just need to, see what my dogs are barking about. Give me 10 seconds. I'm putting this down. I'm reading the sidebar. Check your work to the Regents questions, then I'm going to read that sidebar because I see a few questions over there. Give me 30 seconds. Okay. Okay. Alright, so I'm checking out right now the sidebar. So rate of exchange is equal, rate of exchange is equal, and it can be solid. Beautiful. I can't type. I need coffee. Sorry. Yes, I completely agree with you. I just finished my coffee and I need more. The rate of exchange, beautiful, beautiful. Okay. I see a question here. This is the blue arrow the catalyst? And the answer to that is no, Dylan. That was just me showing you that the forward and the reverse reaction can exchange. I will be talking more about catalysts when I hit Le Chatelier's principle. Alexa, I'm going to hit Le Chatelier's principle tomorrow. Le Chatelier's principle is a little bit more complicated than what you saw here tonight. Le Chatelier's principle relies on this whole concept that a system is going to stay in equilibrium where the concentrations will remain constant because the rate of exchange is equal, unless something bad happens. and I will talk to you all about Le Chatelier's principle tomorrow, and I probably will need 2 streams to really finish talking about Le Chatelier without overwhelming you. It probably takes me about 2-3 periods of class time to really get into Le Chatelier's and make you all understand what's going on. So I'm not going to rush and start talking about Le Chatelier now. Okay, Le Chatelier is more to this story. And you're going to start watching a couple of videos into PDQ before we talk Le Chatelier next time. Okay, I'm just going to go back to these answers on the Regent set of questions. I'm just going to pause because hopefully you check them. And I'm waiting for you. Is there anything? I'm so sorry. When you said Alexa, my Alexa went off. Tell your Alexa I said hi. Oh boy. Oh god, somebody just started the washing machine and that's what you hear in the background. Could you pause that? I don't know if you can hear my washing machine starting right now. Okay, so I'm going to answer any questions you have on these. Start saying stuff in the sidebar if there's anything you want me to go over on these 20 questions, and then we're calling it a night. I'm exhausted. Start asking questions in the sidebar if there's anything you want me to address from these questions. from these guys. Can you all hear my washing machine in the background? It's like, you know, making noises that sound like shh. Because I'm going to have to go pause my washing machine if you can hear it and it's disturbing you. Okay, so Jordana says, I don't understand where the numbers come in. Question 16 and 18. Alright, let's look at that. 16. Okay. Given the equation representing a system in equilibrium, at which temperature does this equilibrium exist? It's a phase equilibrium. So, well, actually what I'm going to do is I'm going to snip this into Smart Notebook so I can write on it. And I'm pretty sure that they... Okay. my washing machine is getting really loud. Oh, I'm so sorry. Okay, so Jordana said 16 and 18, and that's a really large question, 16. Let's shrink you down. Okay, so Jordana, this is a phase equilibrium. And a phase equilibrium really happens at a physical phase change. That's kind of what's going on. It's the reason why why we have a double-sided arrow at this moment. And what they're saying here is that at this particular moment in this equation, a solid can turn into a liquid. At the same time, a liquid could turn into a solid. And there's only one time really where this equilibrium could happen, and it's when you have solid and liquid simultaneously. So I'm just going to go back to this awful place from the beginning of the year. When would you find a solid and a liquid? Well, this whole part over here is strictly solid. This is strictly liquid. This is strictly gas. This range right here is where we have solid that turns into liquid. And this segment of the heating cooling curve is what we call the heat of fusion section, or the melting section, or the freezing section, or the part where a solid turns into a liquid or a liquid turns back into a solid. And this all happens at a very, very specific temperature called the melting point or the freezing point. There are very few things in this class that you need to know. And if this substance is water, the melting point or the freezing point would be 0 degrees Celsius. That's just kind of like a scientific fact. So I'm going to pause for a second. You are expected to know that the melting point, freezing point of water would be 0 degrees, and that's when you would have an equilibrium between these two phases. The other equilibrium place that you are expected to know would be the liquid to gas equilibrium, which would be happening at the heat of vaporization or the boiling or the condensing area, which happens at another very, very specific temperature called the boiling point or the condensation point. Boiling point, condensation point, those are both points that you are expected to know. And if this question was talking to you about an equilibrium between a liquid and a gas, or a gas back into a liquid, this would be 100 degrees Celsius. And I'm pretty sure if I go looking up to question number 18, it's the same concept. And this is another solid to liquid, so it would have to be 0 degrees Celsius. The only difference here is that none of these answer choices are in Celsius, so you'd have to take it one step further, and you would have to convert it into Kelvin. Okay, I'm going back to the sidebar, and I'm looking one more time. Is there anything or any other questions you wanted me to address from this practice set of questions? Okay. If there's nothing else on this, I'm just going to wait for you. If there's anything else on the sidebar, now would be the time for you to start asking questions. Otherwise, I'm just going to have like a closing quick statement about things, and then we're going to call it a night.
Okay, if you're still watching and you feel good, you have no questions on the practice set, start giving me the thumbs up to let me know that there's nothing else you want me to go over. Can you please go over the chart? Absolutely. I think you're talking about this one, the graph, this one. So the reaction shows, the graph shows that the reaction is in equilibrium after 60 seconds. So after 60 seconds, this is achieving an equilibrium. And what this is basically saying to you is that after 60 seconds, the concentration of NO2 is staying constant, and the concentration of N2O4 is staying constant. The concentrations are not zero, like that would be all the way at the bottom. The concentrations are not equal. That would mean that those lines would be directly imposed on each other. Not what they're saying. They are saying that this line is remaining the same, but I don't want you to say the same, because then people think same necessarily means equal. We want to be in the habit of saying concentration, and we want to associate that with constant, which means that it is staying the same over the course of this duration, not necessarily equal. Okay, well, Alexa, I didn't see you say we're good. Okay, all right, so here's what I'm going to say to you. Tonight we had a little bit of technical difficulty. I now know that if my stream won't start in Chrome, that I should use Firefox, so that should save probably about 20 minutes worth of aggravation. On what you saw, it actually started about 20 minutes before that, so that was like a solid 40 minutes of me trying to figure out what's going on. I figured that out. I also figured out that I need to mute whatever it is that I'm watching you all see, so that it doesn't get crazy. And we all know now how that this is going to play out with the assignment, so I don't need to spend about 10 minutes in the beginning talking to you about that. From now on, I think that we'll be able to stream in about, 40 minutes, 45 minutes, hour maximum. I know that this particular stream is a little bit on the longer side. It's not always going to be that way. So, with that being said, I'm going to shoot you all a text in a few minutes. I'm going to I'm going to post on Turnitin. We're going lab on Wednesday at noon. Hopefully people posted the data in that last data section. I am going to be shooting you a text in Remind. I'm going to have in that text, I'm just going to survey you as to, is this time at night okay? Is it too late? Is it okay that it's this late? Is there a better time during the day that my kids hopefully will, give me some time that I can sit down and talk to you? Or is this an okay time for us to try to talk live from now on, if it can, happen within like 45 minutes and we start exactly at 9? And the other thing I'm going to ask you, or I'm going to shoot you, is a text with a link for tomorrow's stream. Tomorrow we're going to start talking about Le Chatelier, so please do the PDQ before we meet up live so you have a working understanding of how Le Chatelier works. Okay, Dylan says, do you have to send a new link each time? Yes and no. Yes and no. Like, if you have my stream live, if you have my channel, there will always, whatever is coming up in terms of streams, you will see on my channel, so that you just open my channel and you'll see it. But there are people who are not so technologically savvy who, need me to send the link, and I will do that as well. I will be sending a link every time I stream so that I am streaming and the time. And tomorrow it has to be about 9 o'clock as well, just because that's when my kids are going to be sleeping and I'm home with them. And alone with them, that I won't be until later that I can stream tomorrow. Okay? Alright, so I think this is going to be the end. Just gonna wait for all of you before I log off and say goodnight. Just give me the thumbs up on the sidebar that we're ready to call it a night. And I'm gonna turn off the stream as long as there's no other questions that you have. Okay. All right, everybody. I'm calling it a night. I just got to figure out how to turn this thing off. End stream. Okay, good night, and I will see you all tomorrow. Stay safe. Stay home. Stay safe. And I'll see you all tomorrow. Bye.